All right. Oh, so today we are going to be talking about operational amplifiers. I mentioned this device way back on the first day of class. That's not how you spell amplifiers. I'm getting myself confused. Amplifiers or op. So I mentioned these guys way back on the first day of class as the only example of a device containing more than two terminals we were going to deal with in this class. The op amp actually has 8. Okay, we are only going to concern ourselves with a few of them. Okay, so what an op amp physically looks like is kind of a microchip type thing. Okay, it's a black plastic enclosure, and it will either have a small circular indentation in one corner or a larger semicircular indentation on one of the shorter ends. And what this indentation lets you know is where the first pin is. So most op amps, as I mentioned a moment ago, are 8 terminal devices, and they're 8 terminal because effectively you're going to have an even number of terminals on a chip like this. Usually one of these terminals actually doesn't do anything. It is not literally internally connected at all to anything. Okay, so this is what one physically looks like. Older op amps are actually little metal canisters that also have 8 pins sticking out of it. It kind of looks like a spider, actually. But modern op amp chips look like this. Okay, I'm bringing this to your attention because we are going to be doing a lab on Friday dealing with op amps, and it's going to be important that you are able to read a pin diagram to know where to make your connections. The pin diagram is going to look exactly like this, except it's going to tell you what each of those 8 pins do. Pin number 1 is always on the top left-hand corner. So if you orient your chip vertically and the circular indent is in the top left, that's telling you where pin 1 is. If you orient it vertically and it has that semicircular indentation, pin 1 is to the left of that. And then you just go around the device in a counterclockwise fashion, counting the pins, and that lets you know where things are connected. So this is what a practical op amp looks like. For a schematic representation of an op amp, it's going to look vastly different. So the schematic representation of an op amp or any amplifier is a triangle. Okay. For our circuit analysis, we are going to be dealing specifically with 3 terminals most of the time. Okay. So I'm going to put a terminal here with a plus sign, a terminal here with a minus sign, and these are our 2 input terminals. Okay. So we have the non-inverting input is the terminal associated with the positive sign. And then we have an inverting input. That is associated with the negative sign. And then over here on the right-hand side of our model, we have our output terminal. Because we have 2 inputs and a single output, our op amp is what's called a single-ended differential amplifier. Okay, so we take 2 input signals And some sort of mathematical operation occurs between those two input signals, depending on what we have connected to our device. And then we get a single output out of this device, depending on the results of that mathematical operation. The operational amplifier is called an operational amplifier because it does math on signals. And we are going to show you, or I'm going to show you, how it can do mathematical functions like addition, subtraction, taking the average of functions, integration, differentiation, and all that kind of stuff. All of those mathematical functions are carried out literally by using resistors, capacitors, and inductors. So this is effectively one of the first analog computers. It was invented around World War I-ish times, where it was made out of discrete components using vacuum tubes and all that kind of stuff. And over time and the advent of semiconductor technologies, we've made it smaller and smaller and smaller until nowadays the actual chip part of an op amp is less than 1 millimeter by 1 millimeter. And then the packaging is usually on the order of 1 centimeter by 0.5 centimeter so that we can physically touch it and do things with it. Okay. So anyway, so these are the 3 terminals that we are largely going to be concerned about in this class from an analysis perspective. Simply inputs and outputs. So we are going to be looking at 3 terminals. However, there are 4 other terminals that are important depending on the application. So let's do this one in gray. So we're going to have 2 terminals here, and these are critically important to the device behaving as it's meant to. So I'm going to call this VCC plus, and this guy down here, VCC minus. These are power supply terminals, okay? In our analysis, in this class specifically, we are always going to assume that our op amp has enough external power to cause it to work correctly. But in practice, we actually have to supply power to this device to make it work. This makes it what's called an active device, okay? So resistors, capacitors, and inductors are examples of passive devices because they exhibit resistance, capacitance, and inductance, regardless of whether or not they're plugged into anything or whether they're part of a circuit. An op amp only provides amplification if you power it, okay? So that's going to be one of the most fundamental things and mistakes that I'm going to see from you guys in your lab on Friday, is that you're going to either forget to connect the power terminals, or you're going to forget to press the little output button on the DC power supply and make it actually give the device power. So something to look forward to there. The other 2 terminals, and I'll do these in this green color here, are our offset null terminals. Okay. So these terminals exist because microfabrication processes are not fully precise. There are some opportunities for small errors to occur, and you could get an op amp in which, if you applied no voltage at the input, you might get some very, very small voltage at the output, on the order of a couple of millivolts or something like that. And the offset null pins are used to correct that, so that when you apply 0 input voltage, you should get 0 output voltage. The op amps that we are going to use for our experiment do not contain offset null pins, but this is where the other 2 pins for a traditional 8-pin op amp come from, okay? So this is our schematic diagram representation of an op amp and the different pins that it has. What I'm about to do is I'm going to open up a data sheet for an actual op amp, and I want to show you what we are really looking at here. So this is the data sheet for Texas Instruments MU-A741 general purpose op amp. This is the workhorse op amp that's used for a wide variety of applications. For those of you that play guitar and stuff like that, if you ever cracked open effects pedals, I would say roughly 1/3 of them use this as their amplifier stage. Here's our simplified schematic. The power pins are not shown here because it's understood that if you're looking at a data sheet, you probably know that this device needs power. Here's a whole bunch. Here's our pin diagram and all that kind of good stuff. I've tried to represent it, telling you what things are. A whole bunch of parameters about the behavior that don't mean a whole heck of a lot to us in this class, but for those of you that go on to circuits 2 will mean lots of interesting things. And here we go. This is what I'm looking for here. Let me make this smaller. Smaller one more time. This is the functional block diagram for the 741 op amp. So that means this isn't the real schematic. It's just a schematic that's close enough to get the job done. None of the component values are listed. It contains 22 different transistors, which we know next to nothing about at our level of knowledge of circuits in this class. 11 resistors, a diode, which we also know next to nothing about, and a capacitor. So you might be asking yourself, within reason, how the hell are we going to analyze this thing if we don't know what 2/3 of the components in it do? We're not going to look at this terrifyingly large schematic here to do our analysis by any stretch of the imagination. If you go through the entire electrical engineering sequence, and if you choose to take my integrated circuits class as a senior, we will build one of these literally from the wafer up. For everyone else, that is much more expertise than they would ever need for most of their jobs and things like that. So it doesn't particularly matter. I don't have any expectation of any student of mine that isn't a graduate student to understand effectively what all this crap means, okay? You Circuits 1 students for sure don't need to know what literally any of this crap means. Why that's true is because op amps are a fantastic device. They're actually, even a practical op amp is effectively governed by 2 simple rules that have to do with the internal circuitry of this device, okay? So let's come back around and talk about our ideal op amp rules. So rule number 1 is that no current can flow into or out of the input terminals of an ideal op amp. So that means in the analysis that we're going to be doing in this class, this current, which I'm going to label I superscript plus, will always be 0 amps. And this current, which I'm going to label I superscript minus, will also always be 0 amps. In truth, this is an approximation, okay? The operational amplifier has an input resistance that is finite, so it is not infinitely large, but it's pretty darn close, okay? So for the MU-A741, that op amp is made using bipolar junction transistor technology, and it turns out that it has an internal input resistance of somewhere on the order of single-digit mega ohms, so millions of ohms. As long as the resistors that we connect to the op amp are significantly smaller than this, so kiloohm scale, this looks infinitely large. And so effectively no current will be able to branch off and flow into either of the input terminals. There is no restriction about current flowing into or out of the output terminal, okay? So only the input terminals have a zero current flowing into or out of it, right? Our second ideal op amp rule is that no voltage drop can occur between the input terminals. And this can be summarized as V plus must equal to V minus, where V plus is the voltage at the non-inverting input, V minus is the voltage at the inverting input, and so we can say there is always a 0 volt drop between these two inputs. So effectively, whatever voltage is applied at one of those terminals gets copied to the other one. This statement is technically only true for negative feedback op amp circuits, but that's all we're going to deal with in this class. So we are going to consider it to be true at all points in time, okay? The reason why this occurs is because the voltage gain, the ratio of the output voltage to the input voltage for an open loop op amp circuit, which I know you guys don't know what the hell that means, is incredibly large, on the order of hundreds of thousands of volts per volt. So if you put in a microvolt signal to a open loop op amp, you should expect to get something on the order of volts at the output. There are some limitations there that are well beyond the scope of this class, but I just am trying to give you some context as to where these rules are going to come from. So if we use these two rules and our regular plain Jane circuit analysis techniques, KVL, KCL, Ohm's law, things like that, we can analyze any possible op amp circuit that we are going to deal with in this class. So what I am going to do with you guys is I'm going to work your homework with you for this particular class, because these are good, simple examples. And we will go over the rules of analysis in doing so. So let me pull up web work here. And we're going to look at homework number 16, I believe. There are a whopping 6 problems. All right, so give me just a moment to copy this stuff down. So let's see. Negative on top, positive on bottom, grounded. I'm just going to make up numbers here. Like so. Here's our output voltage V out. Okay. So I'm going to walk you guys through the process that I use to analyze almost every op amp circuit. And then when we get to one where we can't use the thing that I'm laying out here, I'll tell you how to handle that. It's a very specific case that isn't, in my opinion, practically seen anywhere, but the person who wrote these homeworks likes to be a jerk. So Our first step is going to be apply op amp rule number 1 and find our voltage V plus. So op amp rule number 1 is that this current is 0 amps and this current is 0 amps. Now we will analyze our circuit and determine what voltage occurs or appears at the non-inverting input terminal. The overwhelming majority of the time, this can be done by inspection, but sometimes you might have to look at a little voltage divider circuit or something like that. So what is the voltage present at the non-inverting input terminal here? Who said that? You? That's correct. It's connected directly to ground with a wire. How could it be anything other than 0 volts? Okay. All right. So that is the voltage present at our non-inverting input terminal because our non-inverting input terminal is tied directly to ground here. Our next step is going to be apply op amp rule number 2 and perform KCL at the inverting input node. So op amp rule number 2 states that if there is a 0 volts applied at the non-inverting input terminal, then there must be 0 volts at the inverting input terminal as well. Now we can apply Kirchhoff's current law. So effectively, this current flowing in has to equal this current flowing out because we know that no current can branch off and flow into the input nodes. So this means that 2 milliamps is equal to the voltage present at the inverting input node, 0 volts, minus the voltage present at the node where the current is flowing to, which is V out, divided by that resistor value of 10 kilo ohms. Our third step is then simply solve for V out, which in this case, V out is going to be negative 2 milliamps times 10 kilo ohms is negative 20 volts. That's our analysis. Those are the 3 steps. Doesn't have to be any harder than that, regardless of how hard I make this thing look. If you do those 3 steps in that order, you're correct. Okay. Now I want to talk to you guys very quickly about a couple of red herring type things that I could throw in here to try to mess with you and what the effects would be. But before we do that, I want to point out something really quickly here. We had a positive source connected to our inverting input terminal, and we got a negative output voltage. That is the purpose of the inverting input terminal. It takes a positive input and changes the polarity of it to a negative output. If we put a negative signal on the input, we would get a positive output. So the inverting terminal is always just going to change the sign and apply whatever amplification or anything that we have. The non-inverting input terminal doesn't change the sign. That's it. All right. So let me ask you guys a question. If I had put a 1 kilo ohm resistor right here, would any part of our analysis have changed whatsoever? Not even a little bit, right? Since we know that no current can flow into the input terminals, that means there can be no voltage drop over the 1 kilo ohm resistor, so it might as well not even be there. There are practical reasons why you would put this 1 kilo ohm resistor here, but from a circuit analysis perspective, it doesn't actually do anything, okay? What if we had put in what I'm going to call a load resistance connected between the output terminal and ground? Would that change our analysis in any way? Absolutely not, right? So it does not matter what the impedance is connected between the output node and ground, unless it's a short circuit, we can treat it as if it were not there. If it's a short circuit, then obviously the out is 0 because it's forced to be 0 by connecting it to ground, okay? So the presence of either of these pink resistors does not change the analysis that we would do on this particular circuit at all, all right? So let's look at homework problem number 2. I believe it is literally the exact same problem, except that we now have a voltage source connected between our non-inverting input node and ground. Bless you. All right, so this is the circuit that we are going to analyze now. Again, just making up numbers. Step 1 is the exact same thing that it was. We apply op amp rule number 1 so that we can say 0 amps flow into either of our input terminals, and then we solve for the voltage V+. So what's that going to be? 2 volts, because it's connected to a 2-volt source. Seems reasonable. Op amp rule number 2, or excuse me, step number 2 of our analysis is to apply op amp rule number 2, which means there's also 2 volts at this node, and then write a KCL equation at our non-inverting input node. So this current is once again equal to this current, and then we write our KCL equation. So that's going to look like what? Somebody tell me what the equation should be. Current flowing in equals current flowing out. How did we do it last time? 0.6 milliamps. Absolutely correct. Oh, what the hell just happened? Yeah. So the only thing that changed is that our potential at our inverting input terminal is now different, but all of the other analysis steps are literally the exact same thing. So since we have 2 volts at our inverting input terminal, that needs to be reflected in our Kirchhoff's current law equation. Okay. Step 3 is to simply solve. So we are going to have, let's do some algebra here. So 0.6 milliamps times 8 kilo ohms is equal to 2 volts minus V out. So we subtract 2 volts from each side, and then we put a negative sign around the whole thing. Is equal to V out, and it should be 2 minus 4.8. If I did my mental math correctly. Check it to make sure, please. So effectively, the voltage present at the inverting input terminal, or excuse me, the non-inverting input terminal gives us a positive thing at the output. The input signal connected to the inverting input terminal gives us a negative thing at the output, and then our output is just the sum of those 2 contributions. Is this analysis remotely difficult? It's not supposed to be, okay? Let's look at our third problem. Here is where things are going to get dumb. And why I say things are about to get dumb here is because this particular circuit is an example that contains a voltage source in what I'm going to call our feedback loop. So our feedback loop is the loop that connects the inverting input terminal to the output terminal. I can think of no practical reason why you would literally ever do this. But from a circuit analysis standpoint, there's nothing wrong with it. It does very slightly screw up our 3-step procedure, okay? So I will never ask you a circuit or to solve a circuit this asinine because it has no practical application that I'm aware of whatsoever, but it is in your homework, so we're going to talk about it. All right, so we have our op amp. We have some voltage source here. So let's make this 4 volts. We have some voltage source here. And I believe we also have some load resistance that's connected. So let's make this a 5 kilo ohm resistor. All right. So our step 1 is the exact same. We will apply op amp rule number 1 and determine the voltage V plus. What do we get? Four volts. And I'm going to apply op amp rule number 1 because I forgot to write that down. So we have 0 amps. and 0 amps. Okay. Now, because we have this goofy ass voltage source in our feedback loop, instead of applying Kirchhoff's voltage law, or excuse me, current law, we're going to wind up applying Kirchhoff's voltage law. So our second step here is apply op-amp rule number 2 and write a KVL equation. Okay. So op-amp rule number 2, we have 4 volts here and here. The implication is that there is a 0 volt drop between these two inputs. So what we're going to do is we're going to write a Kirchhoff's voltage law equation, and we are going to start from this ground, go up, over, and down like so, ending at ground. So if we start at ground and end at ground, we have a valid loop. So what's this equation going to look like? Well, we see the negative polarity terminal of the 4 volt source first. So we have negative 4 volts. Then we have minus 0 volts as we take into account the not voltage drop between our input terminals. Then we see the positive polarity terminal of the 2 volt source. Then we see our 3 kilo ohm resistor times some current I. So let's indicate that. So I am saying that my current I is flowing into this terminal based on the sign that I have assigned to the 3 kilo ohm term. And then I have plus V out equal to 0. So we've got a little bit of a problem here because we have 2 unknowns. I, the current flowing through the 3 kilo ohm resistor, and V out. But one of those things isn't actually unknown. I is 0. Hayden, why do you say that? You're exactly right. Yeah, it is literally that simple. The current I flowing through the 3 kilo ohm resistor has to be 0, because if it weren't 0, that would mean current is leaving one of the input terminals, which violates our ideal op-amp rules. So this term right here doesn't actually contribute anything. From that, we're now ready for step number 3. Solve our equation. And so what we'll find is that V out is equal to 4 volts minus 2 volts is equal to 2 volts. These are our 2 different methods. Any negative feedback op-amp circuit can be solved using the 2 different ways that we've described here. If there isn't a voltage source in the feedback loop, apply KCL in step 2. If there is, apply KVL in step 2, and you'll always get the correct answer. Okay. All right. Yes. So we are subtracting the 2 volts. So we're just applying Kirchhoff's voltage law around this loop, right? So if we start at that green dot on the left-hand side and go up, we see -4 because we see the negative polarity terminal first. Then we see 0, and I put -0 because we saw the negative terminal first. And then we see the positive polarity terminal of the 2-volt source. Then we see the resistor, which doesn't do anything. And then we see our output voltage, V out. If we do the algebra here, leaving V out on the left-hand side of the equal sign, the 4 volts gets moved over. And so it goes from -4 to +4 when we move it. The 2 volts was positive 2 volts on the left-hand side of the equal sign. So it has to be -2 volts on the right-hand side of the equal sign. And then that's why we get positive 2 volts at the output. It's just a difference of those 2 voltage drops, or those 2 voltage sources, based on the polarity of the voltage sources that were applied to the circuit. So KVL has to be KVL. Violating it is violating the law of conservation of energy for our system. Any other questions on this guy? All right. Look at our next problem. This is one of my absolute favorites because it's going to annoy the hell out of you guys. So we have our op amp like so, and that positive polarity should be on top. So excuse me. That's one thing that I have not yet pointed out, because all of the examples that we've done so far has had the non-inverting input terminal on bottom and the inverting input terminal on top. It literally, it really doesn't matter where they're located in the circuit. The rules apply literally the exact same way. We have a short to ground here. We have our feedback loop, which contains some resistance. So let's call this a 4 kilo ohm resistor. We have a current source. Let's just call this 1 milliamps for the sake of argument. And then our output voltage is the voltage between our output terminal and ground. That's another thing that I haven't really talked about yet. All of these voltages at the pins are assumed to be like nodal voltages. They're with respect to ground. Okay, so V plus is the voltage present at the non-inverting input terminal with respect to ground. V minus is the voltage present at the inverting input terminal with respect to ground. V out has been the voltage present at the output terminal with respect to ground. All right, so here is our circuit that we are analyzing. And once again, we're just trying to figure out what our output voltage is. So we don't have a voltage source in our feedback loop, which means we get to do the KCL approach. What is the voltage present at our non-inverting input terminal? All right. So we know that this voltage is 0 volts. Additionally, we know that this current is 0 amps. And this current is 0 amps. Applying step number 2, we apply op amp rule number 2, which means this voltage, actually I had it backwards. It should have been that one first. And now we know what this one is. So voltage present at our inverting input terminal is 0 volts. And now we write a KCL equation. So our KCL equation is going to be (0 volts minus V out over 4 kilo ohms is equal to what? 0. Step 3, we solve. What's V out? 0. Really dumb, yes. Now, a fantastic question that I've been asked before is, what the hell happens to the 1 milliamps? Right? There's a 1 milliamp current source that's pushing current in this circuit somewhere, but we know that none of it can branch off and flow through the 4 kilo ohm resistor, because to do so would force 1 milliamp of current into one of the input terminals. All of the current that is being provided by this source is just flowing into the output terminal, and then it's being sunk to one of the power supply rails if we did this practically, okay? So that's why I talked about very specifically, there is not a limitation on the amount of current that can flow into or out of the output node or the output terminal of an op-amp. There is only a restriction on the current flowing into or out of the input terminals. All right. Sorry, that's the wrong thing. We got our next problem. So this is another dumb one. We have a voltage source in our feedback loop. So let's see, I want to say inverting input terminal here, non-inverting here. Let's make this a 2-volt source. Make this a 3-volt source. Ten kilo ohm resistor. Here's our voltage V out. What do you think the answer should be? We've skipped all the steps. How is this circuit number 16.5 any different from this circuit? Literally the only difference is that it's drawn differently, and the problem 16.5 does not have the 3 kilo ohm resistor in the feedback loop, which didn't actually do anything anyway. We have a voltage drop. There's going to be a voltage source between our inverting or non-inverting input terminal and ground, and then we have a voltage drop or voltage source in our feedback loop, and we found out that it was the voltage at the inverting input or non-inverting input minus the voltage drop of the source in the feedback loop. It's literally the exact same circuit, just drawn differently. So I would argue that this is going to be 2 minus 3 is equal to -1, but we can apply all of our steps here and verify that rather easily, right? So step number 1, if my pen will write. Why won't my pen write? Why won't my pen write? Well, this is potentially problematic, and it's also really dumb because I've changed the battery in this thing this quarter, and I should only have to change it like once every 2 years. Let's save this. I guess I have to use my shitty stylus I ran over with the car. Nope, it's not working either. So this seems like a computer issue, not a me issue. Select the pen thing. I need to restart my computer, I guess. All right, so for those of you who are on Zoom and arguably paying attention, I'll be back in roughly 5 minutes because my computer apparently needs to update as well. All right, I can write again, great. Don't know what the heck happened, but that'll be the problem for later. All right, so step one for this guy would be to find the voltage V plus. So what should that be? 2 volts. So we have 0 volt there. So now step 2, because we have a voltage source in the feedback loop, would be to write a Kirchhoff's voltage law equation around this loop, starting at ground and ending at ground. So that's going to look like -2 volts plus 0 volts plus 3 volts plus V out is equal to 0 volts. Step 3 is to solve that equation. And so we would find that V out is equal to 2 volts minus 3 volts is -1 volts, exactly like we had predicted, because again, this is just the same damn circuit that we saw 2 circuits ago. If we look at homework 16, problem 5, which I forgot to bring web work back up. I believe it is literally the exact same. What class is this? Oh, that's the wrong circuits class. That's why that doesn't make any sense to you guys. Sorry about that. 221. Yeah. Next problem. There we go. So if we look at this guy right here, it's literally the exact same thing that your in-class assignment problem number 1 is. So we'll take a moment to go through this. This is actually more in line with the type of question I might ask on your exam. So we have something like this. Let's make this a 1 kilo ohm resistor. A 5 kilo ohm resistor. A 3-volt source. We have a 10 kilo ohm resistor here. And I'm not sure if this is actually on the circuit or not, but we're going to add it just for the hell of it. Okay, it does look like it is. 7 kilo ohm resistor here. And here is our output voltage. Okay, so this guy arguably looks significantly more complicated. There is more things going on, but we can still apply our same simple 3-step process. Because this circuit does not have a voltage source in the feedback loop, we are going to use the KCL for step 2 method. So step number 1, we identify the voltage present at our non-inverting input terminal. What is it by inspection? 0 volts. And while we're here, we can say that this is 0 amps and this is 0 amps. We know that this is 0 volts and this is 0 volts. That's getting ahead of ourselves slightly. Step 2 is what allows us to say that the voltage present at the inverting input node is 0 volts. Now we're going to write our KCL equation. I'm going to do this in a more traditional nodal-like form. So I'm going to just say the currents leaving my inverting input node all have to sum together to make 0. So that's going to look like 0 volts minus 3 volts over 5 kilo ohms plus 0 volts minus 0 volts over 1 kilo ohm. Effectively, this guy right here doesn't do anything because it's shorted out on both sides. Plus 0 volts minus V out over 10 kilo ohms is equal to 0. In step 3, we would solve this guy and we'll find that V out is going to be equal to negative 10 kilo ohms over 5 kilo ohms times 3 volts is negative 6 volts. So like I said, this is more in line with what I would ask you on an exam. So what I would like to do now is literally show you a question from an old test. Okay. So let's open something up here. This will be the last thing I'll monopolize you guys' time with today. Let's see what I did in winter 2020 for exam. None of those look like op-amp circuits. Let's look at fall 2020. Was this the COVID year or something where everything got jacked up? Here we go. So this is the circuit that I gave on the test. This looks like an ungodly behemoth of a thing, right? But we can actually solve it just using the exact same 3-step rule that we've done to this point. Okay. All right on this, great. So our first step would be to apply op-amp rule number 1. Here's our currents of 0 amps. And then solve for this voltage V plus. Now this is the first instance that we have had where we cannot do it by inspection. So what are we going to have to do? Anybody have any thoughts? So in my opinion, nodal analysis is a little bit of overkill here because we're only really looking at one small section of the circuit to figure out what's going on. So let me ask a question in a slightly different way. Where does that 1.2 milliamps of current flow? Through the 4.1 kilo ohm resistor, right? So all of this current branches and flows through that 4.1 kilo ohm resistor. So I would argue that the voltage drop over the 4.1 kilo ohm resistor is just 1.2 milliamps times 4.1 kilo ohms. And I believe I have a calculator somewhere. Here we go. So we can figure out what that is. So 4.1 kilo ohms times 1.2 milliamps comes out to be 4.92 volts. So what is the voltage drop present at the non-inverting input terminal? Well, Kirchhoff's voltage law tells us it's just 4.92 volts plus 6.1 volts, right? So if we wrote a KVL equation from here to here, where the voltage drop over our current source is the voltage present at our non-inverting input node with respect to ground, we would see that V plus is simply equal to 4.92 volts plus 6.1 volt or 11.02 volts. Anybody have any problem with that level of circuit analysis? Simply writing a KVL expression, all right? So step number 2, apply op amp rule number 2, which means we know the voltage at this node is 11.02 volts, and then write our KCL equation. So that is going to be this current plus this current plus this current equal to 0. So that's going to look like 11.02 minus negative 3.9 volts over 4.7 kiloohms plus 11.02 volts over 5.3 kiloohms plus 11.02 volts minus V out over 3.7 kiloohms. All of this is equal to 0. And then we simply apply step 3, solve for V out. Yes. Thank you. You're absolutely right. There are 2 resistors in series there, and I wasn't even paying attention to that. So you're 100% correct. Thank you. So let's put 3. Oh, no, don't open up mail. What the hell is going on here? 3.7 kiloohms plus 9.2 kiloohms. Thank you, Brody. I didn't even notice that resistor exists, but you're 100% correct. And then from here, we would simply solve for V out, and we'd be done. The exact simple little 3-step process that I have given you guys will work for any circuit I can throw at you. So that's why I taught it that way. All right, that's enough ranting out of me.